Hello. Welcome. Okay, so just before we start, I just want to know who attended the previous session about Quarkus. All right, good. So I'm going to be a little bit fast on the beginning because you already saw that, and look a little bit more into details into Kafka and things like this. So first, let me introduce myself. I'm Clement Escoffier. I'm working at Red Hat. I'm doing a lot of reactive stuff that include Quarkus. And that's what we are going to see today, Quarkus, and how we integrate with some part of the reactive landscape, which is all the messaging and reactive systems part. So the first thing is, who is less than 27 years old? A few, OK. So for those young people, 27 years ago, Java was created. And the world 27 years ago was very, very different from the world we have today. And where we were mostly developing with a complete different set of constraints. We were developing what we call monolith architectures. So what they are? Well, when you develop a monolith architectures, everything runs in the same process. That means that everything runs in the same memory space. The big advantage of this is that it's pretty fast because calling a component to another component doesn't cross the process boundary, so everything is fast. You never have data loss or message loss because it's inside the same process. The problem with monoliths, when they are not necessarily correctly done, or even when they are correctly done, is that to release them, you need to orchestrate many, many teams. Why? Because the code size of your application is generally more than just you need to orchestrate all these people, all these teams to get the release done in time. That orchestration takes time, takes energies, and yeah, it was always tricky. So the result of this is that when you build a monolith, you generally release it once a year, twice a year, but rarely more than this. The microservice approach that became popular a few years ago is trying to attack that problem by saying, well, let's split this business, your application, into a set of software islands, and everything will be fine because all these islands will evolve at their own pace, completely independently from the other island, and everything will be great. So if I want a new feature, I can develop it, and that's it. I can develop it, maintain it, operate it, retire it, without touching the other microservices managed by the other team. So on the paper, it's great. In the real life, it's not that great, because basically this independence is not true. As soon as you provide a service which is used by another service, if you change it, then you have a problem. So there is still this orchestration, but yes, technically speaking, we are a little bit more independent and we can build things a little bit faster. So this business agility, on one side, is great for business, but on the other side, it makes developers realize that distributed systems are hard. Because yes, when you start splitting your things into this software island, you are just building a distributed system. So there is no better definition of a distributed system as the one from Leslie Lamport from the MIT that says that a distributed system is doomed to fail. That's it. You can be brilliant, your distributed systems is going to fail at some point. Failures are part of any systems. So you need to, instead of trying to build a failure-free system that doesn't exist, you will need to embrace those failures, react to them gracefully. So microservices became very popular a few years ago, but if we follow these continuums, we start seeing serverless or function as a service. So in that case, you are not going to deploy island, you are going to deploy really small things, your function, and that's it. So what's the main difference is that in that case, in the function as a service world, by default, nothing runs. So all your resources are free, and so on. Well, nothing runs, that's not true. You have a proxy that is running, that waits for HTTP request, and once they receive the request, find the function, instantiate it, execute it, and kill the function. In that world, in addition to be a distributed systems, it stresses the need for having a very fast startup time. Why? Because if your function takes 1 minute to start for 1 second of execution, yeah, you see, you pay for 11 seconds. That doesn't work. So we need to have a fast startup time. So microservices and serverless have been successful these recent years because there are the combination of many new technical trends. Containers, Kubernetes, and things like that. So who is a Java developer here? Yeah, almost everyone. That's good. So when we take a Java application and we put it in a container, we got that. Yes, it's possible to put a Java application in a container. See? It's funny, right? But it's not necessarily useful and a little bit dangerous. Little bit. And the problem is that Java was designed 27 years ago when containers were not part of the picture at all. They were existing, they were created almost at the same time, but completely different landscape. So, and the problem is that when we build in containers, when we want to run something in the containers, we need to think that we are going to share resources. So, who is a parent here? Who has kids? Okay. So when you have kids and you try to teach them sharing, as you know, it's not that simple, right? Sharing is hard. That's exactly the same for Java developers. The problem is that for years, Java has not been designed for containers. So you can say, yes, but the JVM has evolved a lot, and now everything is fine. Yeah, sure, it was terrible a few years ago, and now it's good enough. But the problem is not only the JVM. The problem is also the whole ecosystem around Java that does not necessarily understand that you need to share the resources. So why sharing? Because containers are not really about isolating things. Containers are about sharing the same set of resources, CPU, memories, file system, and so on, across multiple applications. What you want to achieve with containers is deployment density, using your resources at best. That's what you want. But for this, you need to share the resources, and so you need to use them efficiently. You need to use them while thinking that, oh yeah, I cannot use everything for me because another application is going to use something else. So in the Java world, I say that it's not necessarily easy because for years, that kind of model was used. So a lot of threads to handle your requests. Each thread is 1 megabyte of memory, sometimes even more. It also costs CPU time because of the context switch you need. So it's 10 microseconds per context switch. And all this adds up, and at the end, you are using a lot of resources. So you can say, yeah, but I don't care. I use quotas, and everything will be fine. I can limit my applications to just use the things I believe is going to be used. So the problem is that as soon as you reach your quotas, the container host is going to kill you, period. So that's great. At least it will save the resources. So when you are facing such kind of things, you can do two things. You can think about maybe the execution model I was using was not necessarily great for containers, or you can increase the quotas, which we all did. It doesn't fix the problem, but we all did that. So that's what we had in mind when we were starting to build Quarkus. So as it was said in the previous talk, Quarkus is a stack to build Java applications that are truly cloud native. By this, I mean that any Quarkus application will behave correctly in a container, will understand what being in Kubernetes means, will understand what it means to be orchestrated by an orchestrator, such as Kubernetes and others. It will use the resources efficiently and so on. So at the beginning, our main objective was microservices and serverless architectures because it comes with a lot of constraints. We saw them: startup time, distributed systems, and so on. But actually, it's not limited to that. We can do a lot more with Quarkus. So, but when you think about it, what we achieved in the past few years is not just yet another Java stack, truly cloud native. What we build is a real good Java stack to build better distributed systems. So what does that mean? That means that when you think about that, you don't only need an HTTP server somewhere that exposes a REST API, which is sometimes just an HTTP API, absolutely not REST. You need a lot more than this. You need database access, you need clouds, you need workflow, you need messaging, and so on. And our goal is to provide a stack that lets you build better distributed systems. So today we are going to see all this: HTTP, cloud, Kafka, containers, but we are going also to look into 3 other red words: elasticity, resilience, and responsiveness. That's what define better. So what does that mean? Elasticity means that your system is going to auto-scale itself based on the load, always using the lowest possible resources. Resilience means that when failures happen, and they will, necessarily, it's a distributed system, they will happen, you will handle them gracefully. Responsive is the combination on both. If you can continue to handle the work, handle the load, even under fluctuating load, so elasticity, and even when facing failures, you become responsive. Responsive is what you're trying to achieve. That's what defines better. A better distributed system is a responsive distributed system. So Quarkus is basically 2 main principles mixed in. I'm going to be a little bit fast on that because Stuart and Stefan already covered this. But basically, when you do a traditional Java application, you do build things, Maven package, Gradle build, whatever. You get a FATJAR, EIR file, whatever. And then you do java-jar, blah, blah, blah. Then, at runtime, it's going to locate some resources. Because the ecosystem still has a foot in the old world, there is a good chance that those resources are XML files. So to read XML files, you need an XML parser. Xerces? Anyone? Who loves Xerces? Oh, no one. That's weird, right? But the problem is that, yes, we still need Xerces to read those XML files, even if they're empty, even if they're meaningless. Then we need to do class path scanning, because in Java, we love annotations. But one of the problems with annotation is that to read them, to load them at runtime, we need to load the class. Every time we load the class, in addition to the dance of the class loader, we are going to store some metadata related to this class inside a part of the JVM, which is named the metaspace. And the metaspace is not garbage collected. So you are adding data and data and data, because we need to load all the classes from your class path. Yeah, sure, we can reduce the packages and things like that, but basically at the end, you still have loaded a lot of classes. Once you have done that, you have the meta model of your application, meaning that we know what needs to happen. And finally, we can start the pools, the threads, and so on. Quarkus will do exactly the same thing, but before, at build time. At build time, we are going to load our wonderful XML file, maybe use Xerces. At build time, we will do the class path scanning and find all the annotations. So at build time, I know exactly how my application is structured and what need to run and so on. Which means that at build time, I know I can deduce exactly the set of instructions that are required to start my application. And that's what we inject inside our artifact here. What does that mean? That means that at runtime, I will start way, way, way more quickly. Not because we are smart, no. Just because we do a lot less. Everything has been done before. So everything that is done before doesn't have to be redone here. And boom, we start fast because we do less. It has also a big interest in terms of memory usages, because all the classes that generally are loaded at that phase don't need to be loaded at that phase. The XRSS things that we need there, we don't need it there. So because of this, we are going to reduce the memory consumption. A side effect of this build-time principle is the ability to compile our Quarkus application into a native executable, as you would do it with Go, Rust, C, C++, and so on. So instead of having bytecode, you are going to take the bytecode and compile it into native instruction directly. To do that, we need a compiler. And in the great families of compilers, you are only considered serious compiler if you have at least 5 or 6 arguments. Under that, you are not serious. So the compiler we use is named GraalVM. And believe me, they are very, 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 very serious. That means that beyond the hello world, it's humanly impossible to compile a Java application to native without any help. It's just too hard, too many parameters, too many arguments, too many limitations. Quarkus has, during the build time, during that phase, collected many data about your applications, and so can configure your GraalVM compiler to create an optimized native executable. Optimize is important here. We have seen competitors doing the same thing, but taking shortcuts, making compromises. We don't want to make compromise. We want to have the most optimized native images. Why? Because if you use native, it's for 2 reasons. Memory and startup time. If by making compromises you extend the memory usage to be the same as a JVM application, there is absolutely no point going to native. There is many limitations in native, and one of them, which generally Java developers understand, is that in Java, debugging is easy. In native, debugging is GDB. Who remember GDB? Yeah, it's great, right? Amazing experience, especially when you come from the Java landscape. So anyway, you should not consider that native is definitely what you need. It's a nice thing, but analyze before going there. So now I'm going to talk about the pink or red wheel here. So by default in Java, the imperative execution model is the following. You have an HTTP server, for example, you receive an HTTP request, and you are going to assign a thread from a worker pool to handle that thread. That thread is going to handle that request from the beginning to the end. Simple. What's interesting in this model is that the development model is very, very simple because things are executed sequentially. But we are building distributed systems. So there is a good chance that at some point, your request processing will need to interact with a database, another service, or something like this. And in that case, well, you will block, meaning that your thread is going to be blocked waiting for the result of that I/O. So if you want to handle a concurrent request at the same time, then there is no choice. You need a second thread, which will handle another request, and so on. So that means that the level of parallelism, of concurrency of your application is limited by the number of threads you have in the worker thread pool. But what we said at the beginning, threads are expensive. They are limiting your deployment density. They are not making your application very containers friendly. So that model is easy to work with, but not necessarily resource efficient. The competitive execution model is a reactive execution model. In that case, we are taking a completely different approaches where you have a very few threads that we will call I/O threads or event loops. For people that are doing Node.js, that's exactly this model. You will receive a request, start its processing, fine. But when you have to do an I/O, again, database, other service, and so on, instead of blocking, you are going to use the operating system mechanism to schedule that I/O and associate with that I/O a continuation. A continuation is a block of code that is going to be called when this I/O completes, successfully or not. So how it works? So we get the request 1, bam, we need to do I/O, we schedule the I/O, pass the continuations, the thread is released, so I can handle the request 2 with the same thread. right? It's not a different thread, it's the same thread. Request 1 is still in progress, but I'm waiting for some results. When my event loop is idle and I get the continuation, the I/O from the request 1 is arrived, then I will just call the continuation on the same thread, and so on. So this model scales a lot better, is a lot more resource efficient, but we need to use this I/O scheduling and passing continuation. Passing continuation is not natural from a Java developer. You can use callbacks, but no one really wants to use callbacks. We can use reactive programming, you can use coroutine and things like that, but basically, at the end, it's always a little bit more complicated than the imperative execution model. What you need to understand is that the core of Quarkus, everything is reactive. All your I/Os are going to go through neti and vertex, which is a part of our reactive cores, and so you have I/O threads, and then you have extension, and then you have your application code. Does that mean that you need to write application code using continuation and things like that? No, not at all, because basically, Quarkus can detect if your endpoints are imperative or reactive. Depending on the signatures, on the set of annotations and heuristics, we can detect that at build time, and so we know if we need to switch to a worker thread or not. So what's the advantage of doing this? All the bottom of the stack till the routing layer is still executed on the I/O thread, which means that you have a lot of advantages doing this. There is no thread pools, nothing, until you have to reach, until we call the function, and the function will be executed on a worker thread. When the function completes, then we will switch back to the I/O thread and so on. However, if this is not enough for you, if you really want to go to the reactive routes, no problem. Inside the same application, you can just have few reactive endpoints, the ones that are hammered a lot, for example, and then you just use the reactive programming model we provide in Quarkus, so Mutiny or Kotlin coroutines, or you annotate your method with @non-blocking or something like that, and automatically Quarkus will understand that these endpoints are reactive and we will stay on the I/O thread. Max concurrency, best resource efficiency. Okay, so let's not talk about Kafka. So there is a bottle of rum here. Who is using Kafka? All right, I'm going to change your mind. Ready? Go. So Kafka is becoming very, very popular over the past few years because it's becoming the backbone of most modern systems. So the idea behind Kafka is to manipulate the data while the data is still in motion between the collection point and where it is stored, the data lake. And we will do processing and things like that. At the core of Kafka, there is a record. A record is a key-value pair, very simple. The key can be null, the value can be null, and the key and value can be null together, but there is absolutely no use case for that, but you can do it. Anyway, so on the producer side, you are going to create a producer record, which has a topic, a key, and some data. As I said, the key can be null, so you can have just a topic and some value. So here I'm just using strings, but obviously you can use any type of object, meaning that there is a serialization mechanism which is going to take your object and serialize that to bytes. On the consumer side, you get just a record with the type of the key, type of the value, and now we have, and you can get the key and value and so on and manipulate that. It will be deserialized automatically. All right, so these records are returned to partitions. Partitions are log files, so append-only structures, which means it's pretty fast to write because we know exactly where we need to write. We will always write at the end of the file, so we can have a cursor and we know exactly where we are going to write. These partitions have numbers, so 0, 1, 2, 3, and so on. They will have records, which will have, they will be enumerated using an offset, 0, 1, 2, 3, and so on. And partitions are what are replicated, meaning that you can, if you have multiple brokers inside your Kafka systems, which is a good thing, to avoid data loss when one of the Kafka broker crashes, you want to replicate your partitions. So saying, yeah, this partition is going to be there, and a replicate is going to be on another broker, meaning that every time you write, there is a replication kicks in and so on. The notion of partition is key here because that's also what limits your concurrency. We're going to see that. Your partition are grouped into topics, and each topic can have one or multiple partition. And as I said, it's what limits your concurrency. To write, no problem. Basically, when you write, Kafka will deduce on which partition it needs to be written. When you read, that's a little bit more complicated. You are going to poll the records, so it's not a push, it's a poll. And basically, consumers, so these things that poll, will be organized within consumer groups. Inside the consumer groups, basically application, each consumer instances that subscribe to a topic they will share the amount of partitions. So each partition is assigned to a single consumer per consumer group. So if you have two partitions, like in my coffee topics here, and you have one consumer, fine. This consumer will get the two partitions assigned to him, and he will just get all the records. If you have two consumers, okay, then each consumer will get one. Great. If I get three consumers, well, the two first consumers will get one each, and the third one can go in vacation because he won't receive anything. That's how it works. So basically, the number of partitions is your max level of concurrency. So Kafka is simple. If you go to the website and you follow things and everything is fine, at the beginning I say, hey, this thing is pretty cool. It's so simple. So you do a Kafka producer. Great. OK, it uses a config, which is a map string object. Why not? But yeah, OK, I can do that. And then to write, oh, so simple. You do producer.send, new producer record, topic, the key, the value. We're good. And to return the features, oh, that's asynchronous. That's cool. That's exactly what I want for my reactive things. Like, I want to build better distributed systems. That looks like a great thing. Except that when you click on this, and you look behind the hood, that's what is happening. So the first thing is that the producer is going to wait for some metadata of the cluster in a blocking fashion, because he needs to know what are my topics, what are my partitions, and so on. Then he needs to serialize the keys and the values. And this is also a blocking mechanism, because it may need to call a schema registry or something like that. So it's going to do this. So you have the byte array for the key, value, and so on. And then it will call the partitioners to know on which partition I need to write. It can be on the partition 0, 1, 2, 3. This is also something that can be blocking because the partitioner have access to the cluster API. And then something that a lot of people ignored is that the write is not immediate. Your writes are accumulated into a batch of topic partitions, and you have a second thread, an IO thread, which is going to poll those batches, which are complete, and do all the write and all the network things and so on. And it's when this write completes, then you get your record metadata. But all the first part of the process is completely blocking. Second part is not blocking. So it returns the features, but it's still blocking. You need to be aware of that. We were surprised by such kind of behavior. You can say, well, consuming is easy. Consuming is easy because if you follow the rules, you will do something like that. You have your map, you create a consumer, you subscribe to a topic, and then it's written like this. You do a while true, you poll, you max your poll to 1 second, or whatever time you want, which means that after 1 second, it will return the batch of records. You poll by batch, so you get a set of records every time, and then you process them. Processing records means writing to DB, writing to another Kafka topics, well, whatever you want. At some point, you need to inform Kafka that you processed all those previous records, so if you crash and you restart, you will restart from that position, so that offset, and not from the first offset. This poll method is actually very interesting, because when we look into that, it shows that we need to think about a lot more things, like, what about heartbeat? We'll see what it means. When do I commit? How do I commit? How do I handle failures and errors? As we said, distributed systems, we need to handle them gracefully. What about backpressure? If I get way too many records and I can't handle them anymore. What about rebalance, which is what is happening when I have a new consumer in my consumer group that arrives, or when one of the consumer disappears because it's dead or whatever. When we look at the poll method, is what is actually happening. Fetching the records is a blue box. Everything else is actually very, very important. So the first thing you will do is try to connect to the broker to find the coordinator of the group, which is one of the broker which will coordinate the consumer from the consumer group. That broker will start with a consumer a heartbeat protocol, which means that if you don't call Paul again during that period that you defined, the coordinator will consider you dead, meaning that you will not get any more records. You can try to call Paul, won't work. You can try to commit, won't work, because you didn't call Paul enough. So once you do that, you join the groups, there is rebalance happening and so on, fine. You get the assignment, you reset the position, and you fetch the records, and finally you get the records. But the thing is, when we process the records, so we need to call Paul frequently enough to avoid being killed. But on my machine, it's very fine. If I get records, I write to a database, everything runs on my machine, everything's fine. I don't have latency between me and my database. But in prod, imagine that you are retrieving 500 records, which is a default, and you have a latency between you and your database. Well, you are going to block and wait, and boom, you forget to call Paul, and you're dead. The coordinator will just say, no, you didn't call Paul fast enough. Why? Because you were busy writing to your database. That's it. So you can say, yeah, let's switch to asynchronous so I don't have the problem. Oh, you do have another problem now. When do you commit? Because that's the whole thing. Commit management in Kafka. When you have your topics partition and you read it, you can say, OK, 0 and 1 has been processed successfully. But I have also pulled in my land badge 2, 3, 4, 5, and 6. So for Kafka, you're here, but you only committed here. So the last committed offset, and that's something, is the last processed offset plus 1. You can be sure you will have a plus 1 wrong when you do Kafka at some point. It's weird. So that means that if I process asynchronously, and I got 3 and 4 processed, but not 2, I cannot commit 4. Because if I commit 4, it considers that 2 has been processed correctly, while it's still not the case. So we will need to track all this stuff. And believe me, to have done that code, it's complicated. So that's exactly what we try to do in Quarkus, is hide all this complexity without limiting your flexibility. So for this, we're using a middleware which is named Reactive Messaging, which its goal is to build event-driven architectures. And at the core of event-driven architectures, you have the notion of event-driven microservices. An event-driven microservice is consuming events, messages, and producing events or messages. So how it works with that middleware in Quarkus, so you have connectors that will connect to your messaging technologies, such as Kafka, RabbitMQ, whatever. And you have outbound connectors that will do exactly the same, but to write. Your application is structured among a set of beans, which will be event-driven beans. And these beans will receive the messages from channels, which are virtual addresses, produce events or messages to channels, which will be consumed by another beans, until the last channels is just pushed to the connector. So the notion of channels, which is these virtual addresses, is key, and just it's how things will communicate. So in terms of code, how does that look like? Well, if you want to read from orders and want to write to queue, you will write this. I want to read with @incoming from orders. I want to write to using @ongoing to queue, and I need to say to Quarkus, hey, this is a blocking process because processing an order to create a beverage takes time. We will see why in a few minutes. When the processing is done, the reactive messaging and the Quarkus will implement an hack chain meaning that when you write the message to Kafka or to a database or whatever, we will acknowledge the message, which will acknowledge the message, and so on, and so on, and so on, until we reach the inbound connector, which will apply an ACK strategy. The ACK strategy is the CINI that will track your records and decide when and what it can commit. So how does that work? Well, it's exactly what I said before. That means that it will pull only if it will commit only if everything before has been processed successfully. So we will track, and as soon as we have a sequence of acknowledged and so processed correctly records, we can commit that position. We don't commit too often, because committing too often is introducing a lot of load on the Kafka broker. So we commit only every 5 seconds. But what about poison pill? So poison pill is a record that you can't process. That's it. It just crashes. Doesn't work. The problem is that with tracking our offset, if I have my offset 4, which is a poison pill, while it can be committed, that's what is weird, because 3 has been processed, 5 cannot be committed because 4 will never be acknowledged. So a poison pill. In that case, we need to have a mechanism that prevents you from that. Because basically what it means that your application can't make any progress. So if you continue polling and polling and polling, what will happen is that you will just use all your memories. All your memory means also that the memory that you use that should have been used by the other application from the same host cannot be used, so it's pretty bad. So what we do in that case is that we detect such kind of things and I'll automatically mark your application on unhealthy if after 60 seconds your record has not been processed successfully. Of course, this timeout can be configured and so on. But changing this timeout is a very, very bad smell. So we also have negative acknowledgement when a failure happens. And when a failure happens, like this beans fails, then we will automatically knock the message, knock and so on, and then we have a knock strategy. But in Kafka, there is no knock. That doesn't mean anything. So we can fail fast, we stop. OK, fine. We can ignore the failures. Don't do this. But, well, we have it. Or we can write the records to a DLQ, meaning that you already plan that something or someone will read the DLQ later. The problem with DLQ in Kafka is that Kafka is very keen in keeping the orders. If you write to a DLQ, orders doesn't matter anymore. So it's not necessarily sure of what you want. So if you use Kafka, the only thing you can do is fail. That's the safest thing you can do. Of course, you can retry. You can retry, and for this, you will use a small y fault tolerance annotations, like fallback, timeout, and circuit breakers, and so on. But only retry if you know what you are doing. You may break your system because you are creating duplicates. So, in general, do not retry without having checked that you can really retry and your whole system is idempotent, which is rarely the case. So how to retry? Well, you just add the @retry and you're done. That's the beauty of it. Most of the time, we need to bridge HTTP and messaging, and in that case, we will use what we call an emitter. So an emitter is just an object that we will use to emit things on the channels. Here, we are going to emit orders on the channel orders. Or I use it, orders.send. That's it. We have the same thing on the other side, but we're not going to cover that for time reason. So what about backpressure? It's one of the key aspects of better distributed systems or reactive system is how things keep pace. So everything is, no part of the system is overflowed. So we are using reactive streams, which is one way to manage backpressure, not the only way, but it's one way. It's a non-blocking and asynchronous backpressure protocol. So what it is? Well, it's relatively simple as soon as you do data streaming. When you have a producer and a consumer, and producer sends things, then everything is fine if the consumer can process these things at the same pace. So if everything is fine, everything is fine. If your consumer is fast enough, voila. However, if your producer starts to emit a lot more data, and your consumer can't consume, then you will need to buffer your things. Buffering means using memory. Using memory is bad. We have seen that. That reduces your deployment density. So you should not do that. So what can we do? Well, we need to have signals that say that the consumer say, hey, come on, I can't handle more, so please stop. However, in Kafka, it's not that simple to do this. So what we are doing is basically your application, which limits your capacity because you write to a database or whatever, need to inform Kafka that it can't handle more. And for this, we're using pause and resume cycles. So basically, we tell to Kafka, oh yeah, I'm going to pause that subscription. We still need to call Paul periodically. We just say to Kafka, yes, I'm going to call Paul, or I will be dead, but don't send me any records back. I know, it's weird, but that's how Kafka was designed. When you still have the capacity, we will resume and get the things back, and everything is fine. So time for some code, because end of talking, and it's time to do some live demo. So we are going to use a reactive coffee shop demo that you can find at this URL over there. And basically, there is two types of coffee shops these days. There is the old-style coffee shops that you have here, where you go see the bartender, you ask for an espresso. The bartender goes to the coffee machines, prepares an espresso with love and time, because it takes time to do good coffee, and then brings that coffee back to you, you pay, and so on. Great, except that during that time, a couple of customers queued behind me. Not really reactive. New type of coffee shops is where you go, you enter, you see someone, and you do your order, okay? They ask for your name, which is weird. They misspell it, writing it to a cup. You can't believe how many weird way Clement has been written in such kind of coffee shop. And it's kind of rude, but then they tell you, hey, go over there and wait. So you go over there and wait. So you wait, so you, as a consumer, is waiting. But the key thing is that they can handle other orders during that time. And they will write lots of cups with lots of misspelled name that they will add to a queue, and you have baristas that will just take that and prepare your beverage. Right? So we will see the two things. All right. Oops. So my coffee shop should be started already, like this. So I go there, I enter my name, and the first thing is that I'm going to take an espresso from a regular coffee shop, so HTTP, which is completely blocking, so during that time, nothing else can happen. So what will happen is that, yes, it's working, but I cannot order another thing. It takes time to get a good espresso, right? If my barista is down, then I cannot get espresso at all, and my orders are lost, which is sad, because I need a lot of espresso. So how is that done? So if we switch to the code, so this is a Quarkus application, which use a few extensions. So this is to call my HTTP barista. This is to serve the coffee shop. And there is this one. This one is a Kafka connector for Quarkus, which will do everything we just said. So ACK, NACK, throttling, and so on, the backpressure. It also comes with a dev service, meaning that you don't need to have Kafka on your machines. As soon as you start an application using that connector on your machine, it will start Kafka automatically. It doesn't start any Kafka. It will start what we call, where is that? No, sorry, here. It will start Red Panda, which is a C++ implementation of the Kafka protocol. We have also options to start Streamzy instead. The advantage of Red Panda is that it's pretty fast to start. It takes 1 second to start, while a regular Kafka takes around 10 seconds, even if we optimize it. So, all right, so I do this, here. Fault tolerance, we are going to see that. So my coffee shop is implemented that way. I have my barista service. My barista service is a REST client, meaning that I don't want to have my code polluted with HTTP code and so on everywhere. So I model my HTTP interaction using an interface, which we call a REST client. Okay, and again, because distributed systems are doomed to fail, I'm going to protect myself against timeout and call this fallback, which means that I won't get my beverage, but at least I get some feedback that, yes, sorry, your espresso is not going to be delivered. How to use this? Well, you just inject it, and, well, you get your order, you return the beverage, which is just by calling the remote client, and boom, you're done. So how we will do the same thing for the new type of coffee shops. So we are going to send 2 events, and for this, because I'm receiving an HTTP request, I need emitter. So I'm going to create a first emitters which will send orders on the orders channels, okay? And I need another one which will be on the queue channels. I will explain you why, which will be an emitter of beverage, and I will call that queue. So why do we have these 2 things? So orders is what is read by the baristas. The queue is this part here. So it's where you see where is your beverage. Because you can be sure that when you go in such kind of things, you order your beverage, and people that came after you get their beverage before you, right? And you don't understand why, because you were first. That will give you some idea of where you are. OK, so I have my 2 emitters, and now I just need to send my messages to Kafka. So I will do the orders.send, orders.send, order, I'm done, and then queue.send, and now I need a beverage. I just said your orders is queued, and that's it. The first one send to the barista, the second one send to the dashboard that our beverage has been queued. So now with this, I can go back here, sorry. Yes, that's the local one. OK. I go into this new kind of coffee shops. I give my name. They misspell it. And I'm going to ask for latte. Lots of latte. So the thing is, I don't have a barista at that moment. But it's not a problem, because I've sent the records to Kafka, and Kafka has durability. So it's there, just that no one is processing them. So because we need to implement the other side. So let's do that. I'm actually going to start it. Oops, where it is. Yes. So I'm going to start this second application in dev mode, and it will automatically detect that I already have a Kafka broker started in the other one, and will connect. Because if every microservices will start its own Kafka, that will be a little bit stupid. So if I do this, oops, sorry. Yep, here. I just need to do at incoming, orders, at ongoing, queue. It's a blocking process, beverage. Process, order. And here we just do return a method I've prepared, which is just prepare the thing. OK, all right. So now with this, where is my, here. It should start, does it? Yep, let me refresh. So misspelled it. And now it decided that something was wrong. Let me check. Oh, yeah. Let me try it very quickly. So anyway, once you have this, you may wonder about the configuration. So the configuration is actually very, very simple. There is none. The only thing you said is if you want to map a specific channel to a topic, you have this. Everything else, serializer, deserializer, and so on, will be automatically deduced from your configuration at build time and discovered for you. So you don't have to configure anything. So does that work now? Yes. So we have Jacobs processing things. So of course, here you don't really necessarily see the elasticity of things and so on. So just to finish it, I've also deployed my system into OpenShift here. Oh, so with this, with that resolution, it's going to be a little bit weird. Okay, so yeah. So what's important to see is that this is my coffee service, this is my barista service, and this is my Kafka barista. And here, I don't have any pods. I don't have any baristas at that moment. So if I go there and order things, like Frappuccino, because I take a lot of times, nothing will happen, because I don't have any baristas. But if I start kind of autoscaler and operators or something like that, that will monitor how many records, how many orders do I have, then it will automatically create the baristas for me. And now, oops, yes, here, you can see, no, yes, no pod. Refresh. I've seen the order. So it's going to create the number of replicas. So here it's 3. Yes. You see that now we have 3 pods because you have seen that we have orders in the queue. And once all the beverage have been processed, it will kill these pods automatically. So that's great in the sense that it's really on-the-fly resources that you only instantiate when you need that. And so if I go back here, we had Freddy, Charlie, Freddy, and Amelia that processed me. So if I do another run, just to show you, we probably went back to 0, I order a lot, and we will see that it would create the consumers and process them. Why it's so slow? Yeah, so it's starting them. It's what we see here. If we go back, yes, now we have Ava, Poppy, and Oliver, which will process my thing. So if we go back here, just to conclude, oops, slideshow. So the famous last word. So we have seen a little bit of Quarkus today. We have seen this morning the CRUD and things like that. Here we have seen Kafka. It's a lot more than this. And if you're interested, you can stay in this room because we will see GitHub apps by Guillaume. We will see how to write an extensions and things like that. So there is a lot more than this. If you want to go further, I will recommend you 2 books. The first one is available for free on redhatdeveloper.com. It's Quarkus for Spring developers. If you are Spring developers, that will tell you what are the differences, what are the key things. And the second one, which is a complete shameless plug, which is reactive systems in Java, which will explain why we put reactive at the core of Quarkus and how you build a better distributed system with Quarkus today. And that's it. Thank you. If you like what you have seen this morning or today, go to the github.com Quarkus.io Quarkus and click on the star button. That's completely useless, but that makes us, the Quarkus team, very, very happy. Thank you.